Good evening. It's great to have you here. My name is Deb Marr. I'm a professor of ecology at Indiana University South Bend, and I'm going to serve as the moderator for tonight's talk. The Our Universe Revealed lecture series includes talks in science, music, and the arts, STEAM for everyone. We feature current research and creative work being done in our region, and this is an opportunity to be curious about ourselves, our world, and the universe. This is a partnership between the St. Joseph County Public Library, Indiana University South Bend, and the University of Notre Dame. Tonight's speaker, Bahram Moasser, it works at integrating the disciplines of science and art, so a perfect fit for this series. Bahram grew up in the Bronx. He received his undergraduate degree from Cornell University and Ph.D. from the University of Minnesota. Professor Moasser worked at the General Electric Research Center for 11 years and then transitioned into academia. He started at Georgetown University, and then in 2016, he became a teaching faculty member in the Department of Chemistry and Biochemistry at the University of Notre Dame. There's renewed interest in integrating the arts and sciences in higher education. Professor Moasser created a course that integrates the fields of chemistry and art, and this course includes reading primary literature at the art-science interface, analyzing works of art at the Raclin-Murphy Museum, and then also conducting chemistry experiments in the lab. A little bit of everything. So integrating science and art offers us unique learning opportunities to develop skills in critical analysis and innovative thinking. And so without further ado, please welcome Bahram Moasser, and we'll learn more.
Thank you, Deb, for that introduction, and thank you for the invitation. I'm very happy to be here. So, as Deb said, I've created a course with a colleague of mine in integrating chemistry and art. So today I want to talk a little bit about that, and most importantly, I want to tell you something about how, and probably more importantly, why. So that begins with a little bit about myself. So I grew up immersed in music, poetry, art, as well as science. So I always loved science. I loved math, science. I loved being in the laboratory. But also, I don't know where I would be without museums and orchestra halls and botanical gardens. They were equally important to me as I was growing up. So for me, over a long period of time, I developed this thought that these different disciplines, art, philosophy, science, are complementary but independent ways of knowing the truth. But over time, I began thinking more about this, and especially as my role as a teaching faculty. I thought more deeply about this, and I thought maybe they're not so independent, that they are in fact connected to each other, that the thought process, the way of thinking in science and in art is not so different. And I began integrating these in courses that I had. For example, these are some of the examples in laboratory courses that I teach. In one laboratory course, we synthesized a dye called Prussian blue. This is the structure of Prussian blue, and we learned about this structure. We learned about the spectroscopy, but also we used it to create artwork. So these are artwork that students created from the compound they made themselves. And depending on the synthesis, you can make it a darker color, a lighter color. You can mix it with different things. You can make variations of it. In a different course, but also a laboratory course, we created cyanotypes. Cyanotypes are also based on Prussian blue. They are based on a light-activated reaction and an electron transfer reaction. So we studied photocatalytic reactions. We looked at light-activated reactions. We looked at electron transfer. But then we used our knowledge to create cyanotypes. So this is a photograph taken by my student who went to the Matterhorn, took this photograph, and he printed it on transparency paper and then developed it in a cyanotype. This is developing a cyanotype using found objects like leaves and flowers and so forth. In fact, this is sitting in the shelf on my office. So anyone who has come to my office will see this sitting there. So over time, I started integrating as much as I could art into the courses that I was teaching, until it came to the point where I thought maybe we can actually create a course that does this. So my colleague and I, Michael Schreffler, and I created a course called Only Connect Chemistry and Art. And it was first taught last spring, in spring of 24. And it will continue to be taught. In fact, I'm already working on improving it, adding to it, and Michael and I were going to make it a continuing thing for every spring, hopefully for a long time to come. And as Deb said, partly this course is taught in a classroom, in a sort of a lecture style, partly is taught at the Raclin-Murphy Museum of Art, and partly it's taught in the Jordan Hall of Science, in the laboratories. So it's not quite a third, but there's a mix of all of these things. There's hands-on, there's lecture or discussion type things, and there's also being in the museum. So the museum component of it, I owe a great deal to Bridget Hoyt, who is the curator of education academic programs at the Raclin-Murphy Museum of Art. I've worked with her for the last 8 years on different projects, and she has been instrumental in bringing the Raclin-Murphy Museum into this course. So let me explain about the title, Only Connect Chemistry and Art. It has a chem course number and also an art history course number. It has no prerequisites. It satisfies what's called an integration way of knowing, which is a core curriculum type of a course. Without a prerequisite, anyone can take it to satisfy their core curriculum. No background in art or background in chemistry is required. Everything is self-contained. But what does Only Connect mean? Only Connect is the epigraph of one of my favorite novels, a novel by Ian Forster called Howard's End. And it enters into the novel at an important point, in a couple of important points. And really what this is about connecting people. Forster implores people in his novel to connect with each other externally, across social divisions, across other boundaries. But really there's a deeper thing here. His aim here is that these external connections would lead to internal connections in the interior, inside people. So this is the inspiration for this course. The idea that the unity of knowledge, the connection between the different disciplines in the exterior world will lead to connections inside a student so that they can view the world in a better way. Hopefully they can view it in a better way, in a more open way, in a more creative way, and hopefully in a more compassionate way. So this was the inspiration for the course and the title of this course. The witch elm, in fact, is a symbol in the book, and a very powerful symbol. It's a symbol of social stability across different divisions, and also a symbol of connecting the past to the future. So all of that is also involved in this course. So this course has 6 themes, and they are symmetry, perspective, light, shadow and negative space, color, conservation and renovation, and the origins of creativity. So each of these are explored partly in a discussion lecture, partly in the laboratory, and partly at the Raclin-Murphy Museum of Art. So I'm not going to talk about all of it. I'm going to leave a lot out. I'm going to focus on those parts that give you an idea of the why. Why connect chemistry with art? What is the benefit and what would students get out of this? So let me talk first about this object. What do you think this is? Sculpture? In fact, this is displayed at the Metropolitan Museum of Art. It looks like a sculpture. It looks like a beautiful work of art. Would it surprise you to know that this is in fact a fan blade of a GE engine? In fact, it's a fan blade of a GE engine that for the longest time had the record for the greatest amount of propulsion. When I was at General Electric, in fact, I worked with some of my friends who worked either on the composite materials that make up these fan blades or on the actual design, on the shape. The shape, in fact, is related to the efficiency of air flowing through the jet engine and so forth. So my point here is that something that looks beautiful often also functions beautifully. Many times in life, things that are beautiful also have a purpose that is a function that is important, beautiful, or in some way, efficiency is created from beauty. So the unity here is not only in creating a unified view, but also in actual applications, in something that can be useful. So let me first talk about symmetry. That is our first topic in the course. Now, symmetry has many meanings. In many cases, it can have a meaning of harmonious beauty or balance of beauty or things like that. But it also has another meaning, especially in science. And that other meaning has to do with the relationship of parts to the whole and the parts to parts of an object, any object. And we can explore that and we can quantify that. For example, let's take this object. This is a falcon-based tripod, which is at the Raclin-Murphy Museum of Art, and we can analyze it from different viewpoints, okay? So let's look at this object from here. We're looking at one of the falcons with its wings spread, and we're facing it head on. Now, if I am looking at it in this perspective, and I move 120 degrees clockwise and look at it, this object looks the same. And if I move another 120 degrees, I'm looking at another falcon head on, and the object looks the same. In other words, this object is impervious to alternate scrutiny. We can scrutinize this object from different points of view, 120 degrees clockwise, and it will look the same. So this sameness under change is a principle of symmetry. In other words, this immunity to different points of view. Now, we can perform the same operation by standing still and rotating the object counterclockwise about an axis going straight through the base itself. So if we rotate counterclockwise by 120 degrees, this falcon comes into this falcon, it looks the same. And we could do it a second time and it'll look the same. So this transformation resulted in something that is indistinguishable from its original. This transformation is a symmetry transformation. The operation is a rotation of 120 degrees about a symmetry element, which is the axis going right through. So a symmetry transformation is something that leaves an object unchanged. Okay? So we can group all the symmetry operations of an object into a collection, and there are many. A transformation has to have an operation, that's a movement, and that movement is about a geometric object, either a line, a point, or a plane. For example, there is another operation here, and that's a mirror operation. If we take a plane that bisects the wings of the falcon and extend this plane bisecting the bowl itself, it will reflect this half the bowl into this half of the bowl. That's a reflection operation. The geometric object, the element, is the plane. So these are the collection of symmetry operations that this can have. So invariance with respect to transformation is the mathematical definition of symmetry. Turns out that this tripod bowl has the same exact symmetry elements and operations as the ammonia molecule. It has that threefold rotational symmetry, and when I say n-fold, the n here means an angle theta, which is equal to 360 divided by n. So threefold means 360 divided by 3, or 120 degrees. Fivefold rotation means 360 divided by 5, or 72 degrees. Twofold, 180 degrees. So this has a threefold rotational symmetry and a mirror plane, just like our tripod. These are two very different things, but they share the same symmetry. They are fundamentally related in the relationship of their parts to each other and to the whole. So one of the exercises that we do at the Raclin-Murphy Museum is we observed the objects of art. So in the class, we learn about symmetry, elements, operations, and all the ways that you can use to describe molecules and learn something about molecules. But a good way to practice with those ideas is to go to the museum and observe artifacts, arts, paintings, sculpture, textiles, and look at their symmetry, elements, and operations. So, for example, one of the assignments was to look at this plate and to assign all the symmetry elements and operations, and then to define a point group. A point group is the collection of all the operations. So we can define every single one, put them all to a group. It turns out that the collection of all the symmetry operations forms a mathematical group. This has to do with group theory, and group theory is really a mathematical way of describing internal consistencies, which is a way to simplify our ideas about symmetry. So they can go into the museum, they can look at all the elements and operations, and these are the symbols for all the elements and operations, and they can group them into a point group. So by observing works of art, they can learn something about fundamental aspects of symmetry that students can apply to molecules. Because as we saw, symmetry isn't only for molecules, it's for anything. And it turns out that you can take different views of symmetry. For example, the coarse view of this plate without the decorations gives you this point group. But if you include the decorations, for example, the acorns, and you can see that the acorns are bent, there are certain symmetry operations that vanish if you look at it at a finer view. In other words, include the decorations and the details. So the view that you have is important to how you describe symmetry, or if you're looking at it from a coarse view, or if you're looking at the fine details of it. That would now become a D8 as opposed to a D8H. So how is this related to art? So we discuss this, we go to the Raclin-Murphy Museum, we look at artwork, and then we compare it to symmetry used in art. Here's an example of an artwork. This is a relief from the Assyrian civilization. This was in the time of the Assyrian king Ashurbanipal. And what it shows is two deities or two magical creatures. I've shown you this. This is a modern reproduction of this, and it's a faithful reproduction. The only reason I show you this is because I wasn't quite sure if this is going to come out with all the details. But you can see it more clearly here, but this is really a faithful reproduction of that. So let's look at this guy. These are two magical creatures that are tending to the tree of life, which has very important symbolic meaning to the Assyrian civilization. And what they're doing is they're tending to it and they're watering it. So each of these creatures has a bucket in one hand and has something in the other hand. It's a spathe. It's really the sheath of the flower of the date palm. And what they do is that they take this spathe into the bucket, and it has water with some oils or something like that, and then they toss the water on the tree. So this is what they're performing. They're performing this ritual. This would have been very obvious and very clear representation of what is going on. But let's analyze this from a symmetry point of view. So let's look at these creatures, and for now, let's concentrate on their arms and forget about their wings, right? So what are the symmetry elements in this relief? If you draw an axis going straight up, this has a C2 rotational symmetry. C2 means rotation about 180 degrees. Why? Because if you rotate about this axis, that arm that is up in the back comes to the front and the arm is up. And the arm that is down in the front goes into the arm that is back in the front. So this has twofold rotational symmetry. You can rotate about that axis by 180 degrees and it'll appear unchanged. It's invariant with respect to transformation. But what is another symmetry element? For now, forget about the arms, concentrate on the wings. If you look at the wings, it no longer has twofold symmetry because the wing in the back that is up, if you rotate it by 180 degrees, would come to the front where it should be up, but it's down. So the wings don't have twofold symmetry, but they do have mirror symmetry. In other words, if you draw a plane, a reflection plane here, the wing in the back is reflected into the wing in the back, the wing in the front is reflected into the wing in the front. So the arms have rotational symmetry, the wings have mirror symmetry. Why would the artist do this? Of all the choices that the artist had, why this? Why have, in one sense, a reflection symmetry, in another sense, rotational symmetry? Why not both of them be the same? We discussed this in class, and students were on it. They had such great ideas, and I think together we came up with a consensus. And the consensus was that the wings, the mirror symmetry in the wings, represent an identity. In other words, these two magical creatures are the same. They're not two different ones. One doesn't have superiority over the other one. They are the same, and they're doing the same ritual in the same way. But what about the rotational symmetry? The rotational symmetry, in a sense, shows movement. Because when you have rotational symmetry, you're imparting to a static object a dynamic sense. And what this is saying is that these two magical creatures aren't just standing there static, they're actually moving around the tree. So they are identical, they're the same, but they're actually moving. This is a brilliant way. I mean, this is a relief. This is carved in, this is a relief. This is carved in stone. How do you show motion in a relief carved in stone? You show it with rotational symmetry. So the same ideas that exist in science exist in art. So there are consequences to symmetry. There are many consequences to symmetry in art and in science. Let's explore one important one. So let's go back to the wings, forget about the hands. We have mirror symmetry, but let me ask you this question. Forget about the hands. If you take the creature on this side, can you superimpose that creature on this one?
With the wings or without them?
Only the wings, not the hands. You won't be able to. That's exactly right. You won't be able to. This is the mirror image of this. But if you bring this guy around, as we said, the wing in the back is going to be up in the front. It won't work. You can't superimpose it. So there isn't a rotation in the mirror world that can make this guy the same as this guy. If an object doesn't have a rotation in the mirror world, that object is said to be chiral. Chirality is an important principle of science, and what it means, essentially what we described, that you have two non-superimposable mirror images. Let me explain to you in a little more detail. These are two replicas of an original sculpture. So the original was modeled after Giovanni di Bologna, and two different artists at later times made replicas, but they made a decision. They made a decision to make this one-handed or another-handed. Handedness is a way of describing chirality because our hands are chiral. Our hands are mirror images of each other, but you can't superimpose them on each other. So that's where the name handedness comes in. These are two handedness of those sculptures, or the scientific term is enantiomers. These are non-superimposable mirror images. So one artist, I don't know the original, but one artist, again in the same way, the hand is up and down. Here, the right is up, the left is down. One artist decided to make a replica that was faithful to the original. One artist decided to make a replica that was the mirror image of the original, but a non-superimposable mirror image. These two are chiral. And of course, chirality has important implications in science. Many natural molecules are chiral. These are two limonene molecules that have the same composition, have the same connectivity. In many ways, they are identical, but for one important feature. They are non-superimposable mirror images, and that gives them very different properties. So the point groups, the collection of symmetry elements that describe non-superimposable mirror images, can be defined. So there are consequences to chirality, both in art and in science. You can see chirality in many different ways. For example, the twist of a DNA. The screw axis goes in one direction, not the other direction. Nature is full of handedness, and only one of the two possible handednesses. But also art. Let me describe to you this kind of a rotation that gives rise to chirality. I'm a native Iranian, and I grew up with Iranian music and poetry. This is a type of a dance, a Sufi sort of mystic dance. And when the whirling dervishes do it, they do it in mass, but you can do it individually in a ceremony called sema. And usually this is in conjunction with poetry and music, a lot of times from mystic poets such as the Sufi poet Rumi. So there will be someone singing the poetry of Rumi. There will be a classical ensemble providing the music. There will be dancers. And all of them together are creating this unbelievable environment where there is this sort of a unity, this sort of a overwhelming idea of oneness, either with the universe, with the beloved, with whatever else you want to think about. Both in the performers and in the audience. It's just an incredible experience to see for yourself. But as far as the dancers are concerned, in every instance, the dancers are twirling, but they're twirling counterclockwise, always. Why? Well, because in Sufi mysticism, the left is associated with spiritual world. The right is associated with the material world. So when they twirl in counterclockwise, they're moving to the left to go to the right. In other words, they're seeking the spiritual world in order to understand something about the material world. Now, they could have done it the other way, and it would have been a completely different thing. The dance would have looked the same, it would look like people twirling, but the meaning of it would be completely different. For example, if you twirled clockwise, in other words, to the right to go to the left, that may resemble something like a materialism, something like a Hegelian way of thinking. In other words, you're moving to the right, to the world, to seek this spiritual world. In other words, you're looking at the reality in the material world as a way to gain access to the spiritual world. So chirality has important consequences, both in science and in art. All right, so we talked about symmetry having to do with sameness, and the sameness under change. But let's now talk about other kinds of sameness. So there are many times that we talk about resemblances. Resemblances can mean different things. They can mean analogies, they can mean symbols, metaphors. There are many things that we call resemblances between different things. One of these types of resemblances is called a representation. So a representation is different from a symbol. A symbol creates the shape of the thing it's describing. A representation creates the idea of the thing that it's representing. And they're fundamentally different from each other. And let me explain to you that difference in this. This is a sculpture that is in the Raclin-Murphy Museum of Art. It's called Mozart 1. It's by Kenneth Snelson. And this is actually the maquette for the sculpture. The actual installation is in a sculpture garden, and it's giant. It would fill up this room. There's actually 3 different versions of them. But it serves the purpose. So I have my students observe this and give their thoughts about what this is and how you can make sense out of it. In my mind, and I don't tell my students this to begin with, but in my mind, this sculpture, Mozart 1, is a representation of an atom. What do I mean by that? Well, after the Bohr atom, the sort of, classical orbiting electrons about the atom, the sort of galactic version of the atom, that picture was annihilated by quantum mechanics. And after that, we don't have a picture of the atom. One does not exist. Even though that image is so powerful, we still use it, this sort of orbiting picture, it's not really accurate. We're now left with no picture of the atom, so we have to create a representation. This sculpture is a kind of sculpture called a tensegrity sculpture. That word is a portmanteau of tension and integrity. Tensegrity. What that means is this object does not rely on gravity to keep its integrity. What is happening is that the compression forces in the rods are balanced with the tension forces in the wires. These are united together. This push-pull of the tension and compression is holding this entire sculpture together. And in this way, it represents the fundamental forces that keep an atom together. These are the electromagnetic forces between electrons and electrons, electrons and protons, protons and protons. They're sometimes repulsive, sometimes attractive. All of these forces are in balance. The kinetic energy versus the potential energy, all of these are in balance to prevent the atom from either blowing apart or collapsing on itself, but remaining where it is. So that's what I mean by a representation. A representation isn't a picture of a thing, it's a picture of the idea of a thing. And for example, if you have a group or parts of an object that have relational things that are constant within them, they have some things, some properties that are constant within them, you can make a representation of those structures. In other words, the relational properties within the elements of this and this may be the same, even though the two things may be very different. This is called an isomorphism. Iso meaning the same or equal, morph meaning form. So having the same form. For example, I've always thought that people who have synesthesia have isomorphism. People who see numbers as colors, for example. Numbers and colors are not the same. One is not a symbol of the other. One is not a picture of the other. But people who have synesthesia see the structure of numbers combining with each other in the same way that they see colors combining with each other. In other words, that structure is preserved, even though the two have nothing in common. That's what a representation is. It's an isomorphism. So when we no longer have a picture of something or a metaphor for it or a symbol for it, we can have a representation for it. And this is an important topic that we discuss in our class. So this idea of sameness extends, for example, to this other sculpture. This is now still at the Snite Museum. It wasn't moved to the Raclin-Murphy Museum, Spool by John Bisbee. And what it is this sculpture is made of nails. And all these nails are glued together to make this collective. And this collective has a form that is recognizable. So to me, this is a representation of water. This is the water molecule on top. And when we talk about water, we are almost never talking about the water molecule. We're talking about water as a substance, because water as a substance exists as a collection of connections between all the water molecules. So all the properties that are special about water, and there are many, water is one of the most special substances on this planet, all the properties of water are to do with the collective properties of water, much less with the individual properties of a water molecule. So in the same way that the nails came together to form a structure, water molecules come together to form a structure. And that's where these properties come from. So again, this can be viewed as a representation. So we've talked about sameness. We've talked about representation. I can tell you that when I was growing up, words were the supreme way of transmitting knowledge. Language was the most important thing. But language wasn't always used to strictly describe something. Often language was used as a representation. In other words, words were related to words, as opposed to words being related to the world. In other words, by connecting words to words, that created in the interior a mechanism in which you can paint a picture of something. Again, it was a form of a representation. So words created pictures of thoughts. Today, images are supreme. Images have basically taken over the world. And now images represent images. Images create pictures of thoughts. But this idea of words and images have always been important to me. They were important in science. A lot of times this falls into metaphor. We describe things we can't really tell by creating a metaphor. That's a weak form of a representation. But oftentimes it's really a representation. It's talking about a structure that is preserved between two things that we're comparing with each other. So this idea of words and images has always been important to me. And one of the exercises we did in our class was I asked students to think about calligrams. Calligrams are paintings or structures that are constructed from words. This is a calligram from an Iranian artist, Raclin-Murphy, and it describes in words, in calligraphy, something that is represented in the picture. This is a very famous calligram by Guillaume Apollinaire. It's called It Rains in French, and it's describing the poem In Rainfall. Very moving poem, even in translation. I'm not very good at French, but even in translation it's a very moving poem. So that's what a calligram is. It's a description that is doubly acting as words and images. And in science, in literature, in art, this has always been an interplay. Words and images have always been connected to each other. For example, this is a notebook page by a very famous chemist by the name of Roald Hoffmann. And in it, he's using images to clarify his thoughts. Even this doodle over here is used to clarify his thoughts. He's comparing this with that, and he doesn't know it yet, but he will in 1965, that this isn't correct. But all of this is the combination of words and images. These are the notebook pages of Roger Penrose, very famous physicist who was very famous at doodling. He was an artist. He is known for the Penrose tilings. He is one of the preeminent physicists of our time. And his notebooks also contain these equations, which are stunning in their elegance. My notebooks do not look like this. Nobody can read my notebooks, but these are almost like fonts. They're so nice. But these represent these. He used images. He used his paintings and his images to clarify his thoughts, to distill them into their meaning, which then he put into formulae and into the structure of the physics that he was looking for and so forth. Same with William Butler Yeats. He thought in images as well. In fact, a powerful image in his work was the gyre and especially the double gyre. Yeats basically believed in dualism. He basically believed in this sort of a dialectic, and this dualism is demonstrated by this double gyre. For example, a thought emerges at this point, and it expands and it grows and it becomes greater and greater and greater until it becomes very large. And at the apex of the blue thought, a point in the red thought emerges, which then expands, and these two are going opposite each other. In fact, you shouldn't look at this as a static image. You should think of this double gyre as a dynamic image. That's the way Yeats thought of it. So he's using imagery to clarify his thoughts about his poetry. So both in art and in science, image and words have always been related to each other. This goes back to Charles Darwin. He described the branching of the tree of life in his notebook with words, but also with an image. William Blake, in his very famous poem, Tiger, Tiger, he says, "Tiger, tiger, burning bright in the forest of the night, what immortal hand or eye could frame thy fearful symmetry?" But here's the rub. He, a lot of times, put poems with his own paintings. He was a painter as well as a poet. Here's the tiger that he's describing. This does not look like a fearful tiger. He was a very good painter. If he wanted to draw a fearful tiger, he could have. What the painting is saying that the words may not is that the fearful here isn't about the tiger. He's talking about something else. The fearful symmetry here is not applied to the tiger, and he's emphasizing this with the fact that the tiger doesn't look like a vicious animal. One of my favorite authors growing up was Bahram Moasser. Still is. I love her very much. And in this book called The Art Lover, she uses about 100 different photographs of doodles, of newspaper clippings, of all sorts of things interjected with her words. She's using words and image to combine to create an idea. So, as another exercise for my students, I asked them to create calligrams of anything they wanted to. A lot of times for these exercises, I would ask my students to create something, a creative work that incorporates the ideas we're talking about, symmetry, perspective, light and shadow, color, whatever it was. And somehow those ideas had to be central to the creative work. They had to add a meaning that didn't already exist. And they had to write an artist statement along with it that described how that functioned in their creative work. Except for this, because the calligram should have been self-explanatory. It didn't need an artist statement. So Lizzie Power created this calligram. This is the main building, the dome at Notre Dame. And if you look closely, what you'll see is that these are all the courses she has taken. So she drew the main building at Notre Dame with all the courses that she has taken, all the activities. She's in marching band and so forth, science, engineering, engineering materials, all these other things, organic chemistry. And it really, really warmed my heart to know that Only Connect, the course she was taking at the time she did this, is at the very top on the dome. I wish I could say that that's what, because it was such a special course, but it turns out that this is chronological. But in any case, I still like to believe that Only Connect belongs at the top. Another topic that we explored was negative space. So how does negative space come into art? Here are two paintings, one by René Magritte and another one by Abbott Henderson Thayer, which is at the Raclin-Murphy Museum. Now let's take a look at this Magritte painting. Negative space and positive space, they relate to, so positive space is the useful part of the painting. Negative space is all the surroundings. You can think of it that way. But in Magritte, you can think of this in two ways. For example, let's take a view of this where you imagine a man in a bowler hat with a trench coat standing on the ledge looking into a dark night. And his trench coat is painted with this picture of a farm. Do you see what I mean? So he is now the positive space. The background is the negative space. He's wearing something that has this painting on it. But then you can look at this in the reverse. If you think of all of this as a wall, and this part of the man as a hole in the wall. So there's a window in the shape of a man, and you're looking into the outside where you see a farm. The negative and the positive space have flipped. But when you look at it in the second way, where the shape of the man is a window and you're looking out of it, all of a sudden, this part becomes vast. In your mind, you see the rest of the farm. You see a vast scenery. Whereas in the positive space where this man was standing on the ledge, you saw a limited amount of the farm. So your eye can see different things depending on how you view the positive and negative space. This painting is one of my favorite paintings at the museum. This is a self-portrait of Thayer. And I asked my students this question when they looked at this. I asked them, do you think this is an unfinished painting? Did he give up? Did he just got tired of it? I think this is a perfect example of negative and positive space. And again, you can see this in two ways, just like the Magritte painting. For example, let's look at an image in which we're looking through a white wall where someone punched their hand through and put a hole in the wall. And there happens to be Thayer standing behind the wall. So the wall is the positive space. You're looking into the interior and you're seeing this man standing there. Now, let's look at it in another way. Let's look at this as the positive, the portrait as the positive space, being drawn on a canvas that is unfinished. So he wanted to finish the canvas by putting some dark paint around it, but he forgot to do it or gave up or something. So now he becomes a positive space, as opposed to we're looking through a window and he's behind it. But how do you see this? I'll tell you how I see it, and maybe you agree, maybe you don't. When I see Thayer behind the wall that's been punched through, I see his eyes soften. When I see Thayer as the positive space being in front, I see a very stern, very agitated face. His eyes change depending on whether you consider him the positive space or the wall the positive space. I don't know if you see it or not, if you agree or not, but that's the way I see it. And this is so perceptive because Thayer, in his own writings, talked about emotional swings. He talked about having bouts of melancholy. He talked about having bouts of high energy. He was describing, even though it was not known, a condition that you would maybe call manic depressive. So he was so self-aware that he was describing this thing about himself and, in fact, painting a picture that essentially showed the dualism of his condition in one stroke. And whether you saw this as positive or negative space, or what you chose to see as positive or negative space. So negative space is a place where other things can reside. Other ideas can reside. In chemistry, that's the same thing. For example, there are many structures in chemistry that are not molecular. In other words, it's not one structure. It's an extended structure. It extends in 3 dimensions, and it is an array of closely packed atoms. For example, take all these atoms, forget about the blue and the red, take all these atoms and consider them oxygens. This is a metal oxide compound. These are all oxygens in an ordered array. That's called cubic close packed. But if you pack them, for example, if you've seen cannonballs sort of laid in a pyramid, that's cubic close packing. You put one layer of cannonballs, you put the other layer in between the cannonballs in the first layer, and then you can keep going and going. So what happens is when you pack him in this way, you have empty spaces. So if you have 3 cannonballs and you put another one in the middle, there's a space between the 4 cannonballs. That's an empty space. That's a negative space. In fact, there are many negative spaces within the structure. Some of them have a shape of a tetrahedron. Some of them have a shape of an octahedron. In fact, in this structure, there are multiple octahedral vacancies or holes or interstitial spaces. These are different names to describe the negative space. And some of them are octahedral in shape, some of them are tetrahedral in shape. What goes inside them? The metal. These are metal oxides, right? We've been talking about the oxide part of it. The metals go into the negative space in these interstitial spaces. And how the metals occupy these interstitial spaces gives them very different properties. Sometimes they occupy the octahedrals more than the tetrahedrals. Sometimes the reverse. These are same compounds, may have same composition, but very different properties. So negative space is something that unites art and chemistry. Another thing that unites art and chemistry is the idea of chance. So, of course, in science, chance has always been important. Many of the greatest discoveries are serendipitous. Things happen by accident in the laboratory. You have to be open enough to recognize something and to take advantage of it, to characterize it, and so forth. But I mean something else by chance. I mean something that fundamentally changed in the 20th century. In the late 19th century to the early 20th century, science fundamentally changed from a deterministic point of view to a probabilistic point of view. So before, things were being described in very discrete, concrete ways. But in the 20th century, we now describe things, now we're in the 21st century, but starting in the 20th century, we describe things as distribution of probabilities. We no longer say that something is. We say it has this probability distribution. So when we talk about a collection of atoms, a collection of molecules, we say that this population is spread over a number of quantized states. We no longer say things like, this substance has this property. The probabilistic point of view brought chance, randomness, probability, all of these ideas into the world. And it's really no coincidence. I think this is absolutely connected to movements in art such as Cubism and Dadaism and so forth. Cubism, Dadaism, all of these things could not have existed at any other time in human existence other than the early 20th century, because there was something in the air, because the physics of probability, the physics of distribution, the randomness, chance was in the air. At the same time, ideas of art and science were merging together, producing new ideas in each, because they were feeding from the same well of creativity. And I have no doubt in my mind that neither the quantum theory, relativity, or Cubism and Dadaism could have existed independently. They were born together and have always been together. So this is negative space, but this is chance. So one of the assignments that I ask my students to do is to create something in which the element of chance was an important feature. We talked about perspective, symmetry, we talked about light and shadow, negative space, and so forth. We discussed chance in art, we discussed this probabilistic point of view, and dance. This is the first time we brought dance in. I feel bad we didn't do dance before, but this is a picture of Merce Cunningham doing an improvisational dance to the music of John Cage. In other words, he's allowing what is going through him, his feelings, his thoughts, to create a unique form every single time he performs this. And the music, by the way, also incorporates chance. So neither the musician, John Cage, nor Merce Cunningham really know what each other are doing until they're actually doing it together. This is where the element of chance comes in. This is another painting by Grace Hartigan at the Raclin-Murphy Museum of Art also incorporating the element of chance in creating this idea. So I asked my students to be inspired by this element of chance to create artwork. So this is a beautiful piece by Rossio. And what she did is she took different constructions that she had made. She ripped them apart into pieces, threw them up in the air, and allowed them to fall wherever they fell. And then she pasted them together where they fell. And then she finished it with finishing touches and so forth. She put finishing touches on the borders and crossed some of the lines and things like that. So she did a little bit of finishing, but the idea was there. The idea was that this was formed by her tossing the pieces in the air, allowing them to fall wherever they fell. So this is a perfect description of what I mean when I talk about the element of chance. So there's a lot I didn't talk about. I didn't talk about conservation. We had a whole theme on that. I didn't talk about a lot of the work we did in the lab. We made some pigments, some inorganic pigments. We made some organic pigments. In one case, for example, we made pigments from bugs. So we used the cochineal bugs, crushed them in a mortar and pestle, and extracted them, put them in contact with aluminum 3+, first made carminic acid and then carmine red, and used that. We did spectroscopy on it, did some studies on that and so forth. Michael, who's an art historian, he talked about the cultural significance of the cochineal bug and the carmine red dye to Columbian or pre-Columbian civilizations, and how they cultivated this in fields. They had fields of cactus, but they weren't cultivating the cactus. That's where the cochineal bugs live, on the backside of the cactus. So they would cultivate them, they would die, they would gather them, they would crush them. So it was meaningful from an art historian point of view, but it was also interesting from the spectroscopic point of view and from creating a dye. So I wish I could say no animals were hurt. We didn't hurt them, they were already dead, but I guess animals were hurt. So I didn't talk about a lot of things, but as I said in the beginning, what I wanted most is to describe to you the why. Why is chemistry and art important to be taught together, to be integrated, and a little bit about the how this was happening in this course. So I'm deeply indebted to Michael Scheffler and Bridget Hoyt. We're a team, we've done this together, and the first go around was really as well as it could have been. There were a lot of hiccups, there were starts and goes, there were disruptions, as happens for the first time around. I think it takes about 4 years, 4 times to teach a course before it becomes the thing it was supposed to be. So there's going to be refinements, there's going to be revisions, but the idea is there, and the motivation is certainly there. I also have to credit my students. We had a class of 20, we capped it at 20. Next spring we're going to raise it to 30. But these were extraordinary group. I don't know how this course would have gotten off the ground without a bunch of incredibly creative, ambitious, talented intellectuals. Anyway, that's all I have to say, but I would love to have questions from you, so thank you.
Did you find the students were more from the art side than the science side?
Yeah, that's interesting. So the question was, where do the students come from? It turns out, for this first time, that a lot of them were chemistry majors and chemical engineering majors. And some of them were art history majors. One was from Mendoza, I think. Let's see, can't remember. But the minority of them were from the art side. Now, partly to change that, I'm not sure why that happened. I think because I knew a lot of students. So I basically knew about 2/3 of the class. So they saw my name and registered, I think. But partly to sort of change that, next spring, we are going to have designated slots for art history. So certain slots for everyone else and certain slots for art history, because that wasn't the ideal composition. And of those chemists and chemical engineers, some of them were artists, and they were very good. Some of them had no art background, which was not necessary. The point isn't that you were assessed based on sort of your, aesthetic presentation or anything like that. The point was the assessments were based on how well you incorporated the idea into the artwork, whatever it was, negative space, perspective, symmetry, or whatever else. And one thing, just to cap that, which I'm very, very happy about, is I was worried about this. I was worried about assessments. I didn't want to make this a writing course. There's already too many writing courses. And I didn't know how we were going to grade things. I mean, you have to give grades, unfortunately. I wish we lived in a world where there was no grades, but that's not reality. So I was afraid of how we're going to come up with assessments. So we started with creative assessments, and that's where it ended. All the assessments were creative works, either by going into the museum and filling in an assignment, locating artwork, talking about it, or by creating things. Most of them were actually creative artwork. So all the grading in this course was based on creative output rather than writing assignments.
So it wasn't about knowing the chemistry?
No. Anything that was taught in this course was self-contained. So whatever chemistry, whatever art history there was completely self-contained. You did not need a background in any of it. I think maybe once or twice I pushed the boundaries a little bit. I kind of get out of control sometimes.
You'll refine that.
I'll refine that. Yeah.
I was wondering, could you tell if there's any change in how the students are thinking, the people that are taking this course? Do they change how they think about things?
Yeah, absolutely. Thank you for that question. The feedback I got was tremendous, and several students pointed to exactly that point. And in my mind, it was really great that the feedback was positive, and this was a course that was good. But it was much more important that this course was good for something, that it was useful. It changed the way students think. In other words, it fulfilled my ambitions for creating such a course, that they were thinking broadly, they were really engaging in this unity of thought, this idea. And going back to Only Connect, the philosophy is if you see connections in the exterior world, that would impact the interior world, that your mind would be changed in the same way. So students commented on that. They weren't very specific about how that change occurred, but they did point to the fact that it caused them to view the world in a different way. Yeah?
What was the most surprising aspect of this for you and the other instructors in the course?
The most surprising aspect, I think, was, I guess I shouldn't be surprised, but the engagement of students. They took over. They basically took over the course. And I was afraid how this is going to work. I was afraid about assessments. I was afraid about the boundaries between too much chemistry, too little chemistry, too much art, all these things. I was fearful of all these things. But I think students kind of just took over. They set the agenda. They kind of set the boundaries. They set the pace. And I'm just really proud of them. And I guess, like I said, I shouldn't be surprised. I know my students. I know them. So I shouldn't have been surprised. But I would say that was the thing I was most relieved about, that it worked so well because students were so engaged. Yeah.
I don't know how to put this really, but do you think the artists were aware of what they were doing with this space negativity and the symmetry probably, but, or were you just able to pick those out of what you saw at the museum or something?
Yeah, that's a great question. I mean, that's always a question in art. Are you interpreting something that matches what the artist thought, or are you interpreting it in a completely different way? In fact, that was an assignment. So one assignment at the museum was that students had to find works of art and interpret it in a completely different way. In other words, in a way that the artist could not have imagined. For example, there's a sculpture that has a Indian deity with multiple arms in different directions, and there's more into it. And one of my students interpreted this in terms of quantum entanglement. The artist could not have interpreted it in this way. That was not intentional, but she made the connection. That was the point. The point was, can you view something in a way completely different than what it was intended? So that's always the thing about art. Are you really thinking the same way the artist did, or are you giving it another meaning? And, well, does it really matter? Because many times, I think in life, in art, and science, things function in a way that was not intended. And I think that's perfectly fine, because it generates in the mind something completely different. You see a sculpture or a painting, and the intention was something else, but in your mind, it triggers something completely different. And I think those are the places where chance comes in, where the idea of letting chance have a role in your thinking comes in, being inspired. I mean, I can tell you, that's happened to me many, many times, where in science, where I read a paper about something and I get an idea about something completely different, has nothing to do with it. Again, I think there may have been a representation. There may have been something here that had a structure that worked in a certain way that in my mind triggered a similar structure that may have worked for something completely different. So whether we're adding ideas or whether it's the ideas that the artist had, we may never know. In Michael's world, where he's an art historian, that's part of what he does. He tries to understand a work of art in context, in perspective, from the cultural heritage to the pigments that were used, to all the other influences, the other artists, the political environment, the art environment, the historical environment. He tries to reconstruct ideas around a work of art from the history surrounding it. So art historians can give you as much information as they can about the ideas. But ultimately, I think it comes down to you.
All right, let's thank Bahram Moasser.
Thank you.
And
I just want to share a few upcoming things. I don't know if this is on your calendar or not, but next week, they're going to start announcing the Nobel Prizes, I think every day next week. In November, we'll have a panel discussion on the science prizes, so chemistry, physics, and medicine. So that's coming up in November. In December, we're going to have one on the James Webb Space Telescope. So that's coming up December 4th. And then there's also the Christmas lecture, which is at the University of Notre Dame. It'll be Dr. Thaler this year talking about communicating beauty and the possibilities of science. So the November talk and the December talk, they'll be here in this room. And then this one will be at Notre Dame. So anyway, with that, thanks so much for coming tonight. And we hope to see you in November.
It actually says Century
It's a
Center now.
Century Center.
oh, right at the top.
Excellent. I guess it's at the Century Center this year. Yeah. Last year, it was at the University of Notre Dame, but I need to forget last year and look at what's happening this year. Yeah. Good catch. Thanks. All right.